In this video, we're going to look at projection vectors and some vector application problems. So first, a projection vector. The projection vector of u, which is the vector PQ, so we're going to call this u, onto some non-zero vector, in this case PS, and we're going to call that one v. So we're projecting vector u onto vector v. And that is the vector PR, which is determined by dropping a perpendicular from Q to the line PS. So what we're talking about here is that when we're trying to do a projection vector, we're projecting one vector onto another. So in this case, we're projecting vector u onto v. So what we want to do is go to the end of vector u and draw a perpendicular down to vector v, or up in the case if it's in that orientation. So you just want to make a perpendicular segment from the end of the first vector to the vector that you're projecting onto. And then I'm going to call this R. Then this vector right here is my projection vector. And then I also have this vector here, RQ. And so we've resolved vector u into these two components, and these are perpendicular components. And so now I know that vector u equals the projection vector, which is PR, and the perpendicular vector RQ. So my formula for the projection vector is u dot v over the magnitude of v squared times v. Remember that the magnitude of v squared can also be written as v dot v, so we could rewrite this as u dot v over v dot v times v. And then this formula will be on your reference sheet, so you don't need to memorize the formula, you just need to know how to use it. So we want to find the vector projection of u, which is the vector 6, 2, onto v, which is the vector 5, negative 5, and then we're going to write u as the sum of the two orthogonal vectors, one of which is my projection vector. So remember, this is u, and this is v, and we're projecting u onto v. So what I want to do, I want to drop a perpendicular from u down to v. And then this purple vector is my projection vector. So your projection vector is always a vector along the v vector, but it's going to be a different magnitude. So remembering my formula, projection vector of u onto v is u dot v over v dot v times the vector v. So I'm just going to kind of figure out these parts of this formula here. So u dot v is going to be 6 times 5 plus 2 times negative 5, which is going to give us 30 minus 10, which is going to give us 20. And then I need the magnitude of v squared, or I need v dot v, which is going to give us 5 times 5 plus negative 5 times negative 5, which is going to give us 25 plus 25, or 50. So now I can do my formula. So the projection of u onto v is going to be u dot v, which is 20, over v dot v, which is 50, times vector v, which is 5, negative 5. So this is going to be 2/5 times 5, negative 5. So we're just doing a scalar multiplication here, which is going to give me 2, negative 2. So the purple vector here, which is my projection vector, is 2, negative 2. Then we also want to find this other vector here. So I'm going to find this black vector here, which is my perpendicular vector. And to do that, we're just going to do a little bit of arithmetic. So we're going to do u is our projection vector plus the perpendicular vector. So remember, u was the vector 6, 2. My projection vector is 2, negative 2, plus my perpendicular vector, which is going to have a horizontal component and a vertical component. So then I'm just going to do a little bit of algebra here to solve. So 6 equals 2 plus x, so x equals 4, and 2 equals negative 2 plus y, so y equals 4 as well. So then we can write the vector 6, 2 equals the projection vector, which was 2, negative 2, plus the perpendicular vector, which is 4, 4. All right, we're going to take a look at a couple of examples of applications of vectors. So you have a jet which is flying at a direction angle of 25 degrees at 500 miles per hour, and we want to find the component form of the velocity. So we can kind of visualize this here. So my plane is flying at a direction angle of 25 degrees, and the speed is 500, so that would be my magnitude. And we're just looking for the component form of this vector. So I just want to use my component form formula, which is, remember, magnitude times the cosine of theta, and magnitude times the sine of theta. So in this case, we're just going to go 500 cosine of 25 degrees and 500 sine of 25 degrees, which gives me 453.15 approximately and 211.3. And that would be my components, my component form of the velocity of that plane. All right, so here's a second example. We have a force of 50 pounds acting on an object at an angle of 45 degrees. We have a second force of 75 pounds acting on the object at an angle of negative 30 degrees. So we want to find the direction and magnitude of the resulting force. So first of all, when you see the word resulting in your question, this means that you're going to have to add the vectors. So again, if we sort of visualize what we have here, is we have this first one, which is 50 pounds acting on 45 degrees. So this would be sort of in here, 45 degrees, and this would be a magnitude of 50. And then we have a second force, which is 75 degrees at an angle of negative 30 degrees, a force of 75 pounds acting at negative 30 degrees. So that would be here. So this is negative 30, and this has a magnitude of 75 pounds. So what we're looking for is the resulting vector, so we want to add those two vectors together. So let's call this one force 1, and we'll call this one force 2. So the first thing that I'm going to do is I'm just going to find the component form of force 1, which is 50 times the cosine of 45 degrees, and 50 times the sine of 45 degrees. Force 2 is going to be 75 cosine, negative 30 degrees, 75 sine, negative 30 degrees. So my resulting force is going to be the two of these added together. So my resulting force is going to be F1 plus F2, which is going to give us 50 cosine 45 plus 75 cosine negative 30, and then 50 sine 45 plus 75 sine negative 30, which will give me approximately 100.31 negative 2.14. So first, if we sort of visualize where this vector would be, my x-coordinate is positive, my y-coordinate is negative, so my resulting force is going to be in quadrant 4. So we're trying to find this direction angle, and we're trying to find the magnitude or the actual force on the object. So once we have the resulting force, then we can find the magnitude of that force. So the magnitude of F1 plus F2 is going to be the square root of 100.31 squared plus negative 2.14 squared, which gives us about 100.33 pounds. So my magnitude is about 100.33, and then I need to find that direction angle. So remember, to find a direction angle, we're going to take the horizontal component. So I'm going to take the 100.31 equals the magnitude, so 100.33 times the cosine of theta. So then theta is going to be inverse cosine of 100.31 over 100.33, which is going to give us an angle of about 1.14 degrees. Now remember, with direction angles, you always have to pay attention to the quadrant, so 1.14 degrees would actually be in quadrant 1, and I know that my resulting force is in quadrant 3, so I know that I really need to take the negative answer here. So my theta is negative 1.14 degrees. So my magnitude is 100.33 pounds, and my direction angle is negative 1.14 degrees. All right, so here's another example. We have a pilot's flight plan, has her leaving San Francisco and flying due east. So if we consider the origin, the airport, and then we're flying due east, so we're flying along the x-axis. There's a 65 mile per hour wind in a direction of 40 degrees. If we kind of draw that in here, that would look something like this. So this is 40 degrees, and this magnitude would be 65. We want to know what direction the pilot should follow and what the plane's speed will be if the speed of the plane without any wind is 450. So since the wind would be pushing the plane somewhat north, we're going to want the plane to be flying somewhat south, so that as the wind pushes it, it will be along that horizontal there that we're looking for. So we need to find this direction angle. So find the direction angle the pilot should follow. And then we want to find the speed of the plane with the wind. So what we know is that this speed, or this magnitude on the actual path of the plane, is going to be 450. And then what we know on this vector here, the red vector, is we know that this angle is 0 degrees. So we have the wind. I'm going to call that vector W. And I know that the angle for vector W is 40 degrees. And I know the magnitude of W is 65. And then we've got the plane, and I'm going to call that P. So the the direction angle for P is what I'm trying to find, so we're just going to call that theta. And the magnitude of P, we know, is 450 degrees. And then we've got the actual flight of the plane, and I'm going to call that F. And I know that the angle for F is 0 degrees, and I know the magnitude of F is, again, what I'm trying to find, so I'm just going to call that F. Writing the component form of each vector up here will give me W is 65 times the cosine of 40, and then 65 times the sine of 40 degrees. The plane is going to be 450 cosine of theta, 450 sine of theta. And then the flight path is going to be the magnitude, or the speed of the plane with the wind, times the cosine of 0 degrees, and then that magnitude times the sine of 0 degrees. Now we know, we don't know the magnitude here, but we do know the sine and cosine of 0 degrees. So the cosine of 0 is 1, so this is going to be F, and then the sine of 0 is 0, so this is going to be 0. And then what we know is that the wind plus the plane is going to equal my flight path. So if we go 65 cosine of 40 degrees, 65 sine of 40 degrees, plus our plane vector, which is 450 cosine of theta, 450 sine of theta, and we know that that equals the actual flight path, which we simplified to be F and then 0. So now taking all of my horizontal components, so we're going to get 65 cosine of 40 degrees plus 450 cosine of theta equals F. Now the problem with this equation is that there's two different variables in there, so I can't solve that one yet. And then over here, we're going to get 65 sine of 40 degrees plus 450 sine of theta equals 0. So here I only have one variable because I have the 0 on the right-hand side, so I can go ahead and I can solve for theta. So doing some algebra, we're going to end up with theta is negative 5.33 degrees. And then once I have that value, I can come and plug it back in over here to find the magnitude. So now we can go 65 cosine of 40 degrees plus 450 cosine of the negative 5.33 gives me F. So F equals about 497.8. So that's my speed. So we get 497.8 miles per hour for the plane with the wind, and we should be flying at a direction angle of negative 5.33 degrees.